Hey everyone, welcome back to another video from the Way Tutor. This video is going to be dealing with trigonometry and circular measure. This is video 7 of the function series, and normally it's introduced in the first part of the methods course in a lot of schools. I think the reason why that is because they introduce the concept of radians, which is a little bit difficult to wrap your head around. Radians are another way of measuring angle other than degrees. But I've introduced it here because I think it fits better within the flow of the course. So let's get into the unit overview. So the first thing I'm going to be doing is I will be having a review of what sine, cosine, and tan are defined as we currently understand it in terms of SOHCAHTOA, and then I'll be extending that into a unit circle definition for sine, cosine, and tan, which is a lot more versatile and lets you deal with angles outside of the bounds between 0 and 90 degrees. I'll then have a look at a relationship between the angle of inclination of a line, so that is the angle a line makes with a positive x-axis, and the tangent of a line. I'll be having a look at some of the trigonometric rules like sine rule, cosine rule, having a look at the ambiguous case in the sine rule, and then also having a look at calculating area of triangles in cases where the base and the height aren't known, for example. So there are other ways of calculating triangles. We also have circular measure and radian measure in this video. We'll have a look at where we get radian measure, which you'll see is very closely related, which is actually a circular measure, and see how we can use radians to calculate certain properties of circles like sectors, segments, and arcs, for example. Alright, cool. So let's get straight into it. Okay, so the first thing I want to do is I want to have a review of the trig functions as we currently understand them. And our current definition of the trig function relates sine, cosine, and tan to a right-angled triangle, right? And so within this right-angled triangle, we have a couple of key sides. I'm currently drawing the hypotenuse, for example. And so we've got our hypotenuse here. And if we have our angle here, we have our opposite side, and we have our adjacent side. And so these sides are labeled relative to the angle theta here. Okay, the hypotenuse is always the same because it's the side of the right angle triangle that is opposite the 90-degree angle. Alright, so in this context, we know that sine of theta is equal to the opposite side divided by the hypotenuse. We know that cosine theta is equal to the adjacent side divided by the hypotenuse. And we know that tan theta will be equal to the opposite side divided by the adjacent side. Okay, and so this is our common definition of sine, cosine, and tan. And we have our SOHCAHTOA to remember that. So sine is opposite over hypotenuse, cosine adjacent over hypotenuse, tan opposite over adjacent. Alright, was there anything else I wanted to go over? Yes. When it comes to sine, cosine, and tan, we also have a couple of specific right-angle triangles that help us calculate exact values for some values of those trig functions. And those two triangles, I remember my math teacher always called them the God triangles. I don't know if that's actually the term for them. But you have, I might not just use the rule, I'll just do this quickly. But ideally it would be, so that should be a 90-degree angle. That should also, maybe I'll make them a bit bigger. Okay, so you have this, and you have this. And so the two God triangles are the triangles that have sides 1, 1, and then root 2 over here. And then we have 2, 1, root 3. And so what this one here is it's basically an equilateral triangle that's been cut in half with side length 2. And so if we have a look at the equilateral triangle, we know that that'll be 60 degrees. Because this side has been cut in half, that'll be 30 degrees. And we have 90 degrees here as well. In the case of the 1, 1, we have 90 degrees. This is an isosceles triangle, so both of these sides will be 45 degrees. And so these two triangles are really helpful when it comes to determining exact values for sine, cosine, and tan for those specific angle values. For example, sine 60, or sine 30 degrees, I should say. Sine 30 degrees is equal to opposite over adjacent is 1/2, 1 over 2, or sine 60 degrees is root 3 over 2 for sine. Cos 60 degrees is 1/2 as well. And so you can extend that to these two to either of these two triangles to calculate certain values that are quite easy to compute. And so that's a whole branch of the methods course, is being able to calculate exact values for certain values, certain angles, and it uses these triangles. It uses these triangles a lot of the time. There's also another rule that you can use your fingers somehow, but I've never really understood that. But if that works for you, have a go at that one too. All right, so now we've come to the SOHCAHTOA definition. This is the definition that you've used for sine, cosine, and tan from year 7 to 10, but actually it is a derivation from a much broader definition of sine, cosine, and tan, which is the unit circle definition. And this is the actual definition of the trigonometric functions here. So the unit circle refers to, as you might guess from the name, a circle of radius 1. And here's our x and our y coordinates. And we consider a line from a radius of the circle from the origin, 0, 0, up to the point on the circle, like this. And we have our point 1, the radius 1 here. Alright, and then this tracks down to here, and we have our 90 degrees. And so we can see from this one how our triangle definition kind of relates to the unit circle. If we look here, we have opposite and we have adjacent for this triangle here. And so we know that for sine theta, or maybe I'll do this in red, for sine theta, we have opposite over 1, so just opposite. For cos theta, according to the unit circle definition, we have adjacent over 1, so just adjacent. And for tan theta, as before, we have opposite over adjacent. And in the case of the unit circle definition, that's actually defined as extending the line so it hits a tangent up here. And this is your value for tan theta. I've never really understood that, but that's how it is. In terms of your sine and your cosine, you have, if you look at what the sine is defined as, it's defined as opposite. So if you look at this in a geometric sense, in a Cartesian sense, you can see that your y coordinate will be your sine theta, whereas your x coordinate will be your cos theta. And so this point here will be defined in terms of cos theta, comma, sine theta. And that's your unit circle definition. So according to the unit circle definition, your sine, the sine of your angle will be equal to the y coordinate it makes in the unit circle, and your cosine theta will be equal to the x coordinate it makes in the unit circle. And tan theta is equal to this weird tangent line here. So if we have a look and we extend that, we can actually use this fact, so this definition that sine is equal to the y coordinate, and then cosine is equal to the x coordinate, and then tan is equal to whatever this hits on this tangent line. We can extend that to broader definitions of sine. So if, for example, if we have a look at this one here, and we know that that angle there is theta as well, so that overall the angle from the positive x-axis will be 180 minus theta, we can see that due to symmetry it will have the exact same y coordinate as the original angle. And so as a result, sine of 180 minus theta is equal to sine of theta. And so for example, if we have sine of 45 degrees, Okay, and we know from this unit circle over this God triangle over here that sine 45 degrees equals 1 over root 2. That means that we know that sine 180 degrees minus 45, which is sine 135 degrees, will also be equal to 1 over root 2. Okay? However, cosine, if we look at it here, will be in the negative direction. This is cosine theta, and it's in the negative direction. So cosine of 180 minus theta, cosine of 180 minus theta will be equal to negative cosine theta. Okay? And so we have, in this case, cosine will be a negative value. It'll have the exact same magnitude, as in the distance from 0 to that value of cosine will be the same as in the initial case, but it'll be in the negative direction. And if you look at the tangent line, what we generally do is we always extend the line all the way down to here, and then we get this value for tan. And this value for tan, due to the symmetry, will again be this tan, but because this tan's in the positive y direction, it'll be positive. This tan is in the negative direction, so it'll be negative. And that follows as well based on the fact that tan theta is equal to sine theta over cosine theta. And if sine is positive and cosine is negative, then tan will also be negative. Alright, if we look at this angle here, and we have our theta again, we'll see that sine and cosine are both negative, and they will have the same values. Tan, on the other hand, is positive because it tracks back up. And here we can see that tan is negative, sine is negative, but cosine is positive. And so if we look at it this way, we can see, I'll do this in rainbow, we can see here all of them are positive. Here only sine is positive. Here only tan is positive, and here only cosine is positive. And so you have this ASTC. And you can think of a bunch of different acronyms to try and remember that. This is your first quadrant, second quadrant, third quadrant, and fourth quadrant. Alright, cool. So, if we have this unit circle definition, we know that theta and 360 degrees plus theta will have the same value of sine, cosine, and tan. This is known as the periodicity of the function, and it means that for every value of sine, the pattern that it makes will repeat every 360 degrees. And this is especially important when we're trying to graph trigonometric functions. With regards to tan, we only have a period of 180 degrees. The tan sort of pattern repeats after 180 degrees. If we look here, we can see that initially tan goes up here. At 90 degrees, it is undefined because it's parallel to the tan line. Here, it heads down to the negative side of tan, and then it goes around, gets back to the positive side here. And then, now that 180 degrees has finished, we actually start this entire pattern again, right? And so the period of tan is 180 degrees, whereas for cosine and sine, it is 360 degrees. Alright, that is something that it takes a little bit of time to wrap your head around. So if something doesn't make sense, make sure you're leaving something in the comment section. I'll go over it in supplementary content. And also there's a bit of an explanation in Sadler where you can have a read through and have a revision of what the unit circle definition kind of looks like. Now, let's take a look at the relationship between the angle of inclination of a line and the gradient of that line, and more generally, just trigonometric applications in other areas. So, for example, the cosine and sine rules and the area of a triangle rule. So, angle of inclination of a line. If we look at our line on a Cartesian set of axes, and those axes aren't very well drawn, but ideally you'd be using a ruler, and you have your line here. Maybe I'll move this line over to make it a bit easier. Okay, and we have our line here. This is our line y equals mx plus c. We know that our gradient is equal to rise over run. If I was to draw an angle here, theta, and I figure out tan theta, I know that tan theta, if I draw a right angle triangle like this, will be equal to rise over run. So tan theta equals rise over run. And so my tan theta is equal to the gradient of my line. It's also important that we define tan theta relative to the positive x-axis. Okay? So that's an important fact. If we look at tan theta in this direction, for example, this is 180 minus theta. Based on our unit circle definition, it'll be a negative gradient, which obviously isn't the case here. If we have a line that looks like this, then we know this has a negative gradient, and again, we measure with respect to the positive x-axis. And so we have our value alpha. And so the gradient of this line here will be tan alpha. So hopefully that's relatively straightforward and easy to understand. And so we'll move on to the cosine and sine rules. The cosine and sine rules are generally particularly helpful if we're dealing with triangles that aren't 90 degrees. So for example, this is a triangle that's clearly not a 90-degree right angle triangle. When we look at our triangle, we label A, B, C, and we have angles associated with these. We have sides that are associated. A is opposite the corner A, C is opposite the corner C, lowercase c that is, and lowercase b is opposite the corner B. Now our sine rule will be defined as sine A over A equal to sine B over B, which is equal to sine C over C. And if we rearrange that, we can also see that that's equal to A over sine A, and B over sine B, and C over sine C. As we'll see when it comes to the sine rule, there is actually some cases where you can't apply it with 100% certainty, which we refer to as the ambiguous case, and we'll get to that in a moment. The other rule that we know is the cosine rule, and the cosine rule is defined as c squared equals a squared plus b squared take 2ab cosine c. And both of these formulas are on your formula sheet. Cosine rule and sine rule. And so again, these values and variables refer specifically to those sides of the triangle. C squared, one side of a triangle is equal to the sum of the squares of the other sides minus 2 times those other sides times cos C. And A sine A, B sine B, C sine C are similar. When it comes to the ambiguous case of sine, the ambiguous case arises in cases like this. For example, if we have an angle here, we have a side here, and we have a side here, but we don't know the other angle. If an angle is unknown, that's when the ambiguous case arises. So in this case, we have theta. I'll label this alpha. And these two sides are the same. So as a result, this is 180 minus theta. Okay, so if we have x and we have an angle alpha here, and we have a side y, then there's two sides y here. Because this is an isosceles triangle, both base angles will be theta degrees, and so you'll have 180 minus theta over here. So if you have a case like this, you won't be able to tell if your value for the angle is theta or 180 degrees minus theta, unless you see the diagram. If you see the diagram and you see that it's clearly an acute angle or it's clearly an obtuse angle, that's when you can reject one of these different values. But you also need to provide your justification. For example, I am saying this is an acute angle because I can see that the angle is acute in the diagram. The reason why this 180 degrees minus theta and the theta arises is because, again, tracking back to the unit circle, if you look at your angle, 180 degrees minus theta, and theta will have the same y coordinate, and so the same value, y value. This doesn't apply for cosine, because when it comes to cosine, you have your one value here, and the cosine of 180 minus that angle is the negative value, so they're completely different values, whereas it does arise in the sine case because of the fact that you have them being equal to each other. So remember, the ambiguous case arises when you have two sides and one angle, and so if you're trying to calculate the other angle, that is where the ambiguous case arises, and more specifically in this sort of setup here. Alright, the last thing I'm going to go over in trig is the area rule for a triangle, area of a triangle. And I just wanted to mention as well that all of these properties can be proved. I won't go over the proofs here. That's provided in your Sadler textbook. In the area of a triangle. In the area of a triangle. Okay, in the area of a triangle, we know that it's going to be equal to, if we have a look at another one like this, A, B, C, and we have our A, B, C, then the area of a triangle will be equal to 1/2 AB sine C. So these two angles, these two sides, sorry, and the angle bounded between them, okay, will be equal to the area of the triangle. This is as opposed to 1/2 base times height, which is the general one that we used, and that's one generally used when we know the height of a triangle, which is especially easy if it's a right angle triangle. So a lot of these rules, sine, cosine, and the area of a triangle rule, relate to triangles that don't have right angles, and they're applicable in those scenarios. Okay, next thing we're going to go over, this is an entirely new topic now. We are moving on to circular measure and radian measure. And so the first thing I want to do is I want to define radian measure and understand its relationship with degree measurement. Radian measurement comes from a circle, just like before. If we have a look at a sector of a circle here, so we'll draw lines like this and like this. We have a radius, we have an arc length, and basically this angle here will be defined in terms of radians if the angle theta is equal to the length of the arc divided by the radius. So if I write that out in longer, an angle in radians is equal to the arc length here divided by the radius. So if we have an arc length of 1 and a radius of 1, that means that our radian measurement will be equal to 1. And we can also extend that out. If we double that and we make the arc length double the distance that it is, then we can see that we still have the same angle in radians, because this one basically just increases by 2. It doubles, and this also doubles, and so on and so forth. We can replace this with n and n for any n is an element of real numbers. But yeah, anyway, you'll always have this same value. The main thing that matters is the ratio between the arc length and the radius. Okay. Now, if we think about the relationship with degrees, if we think about a value like this, if we think about 180 degrees, we know that 180 degrees is a straight line, right? So this is 180 degrees. If we consider this as a radius of 1, and then we consider the circumference of the entire circle, that's equal to 2 times pi times 1, which is equal to 2 pi. And if we consider half of the circle, it'll be 2 pi divided by 2, which is equal to pi. So our length of our arc here is pi. And so if our angle in radians is defined as the arc length divided by the radius, that'll be equal to pi over 1, which is pi. So based on this logic, 180 degrees is equal to pi radians. And another thing I should mention, now that we've introduced radians, we always need to indicate this degree symbol if we are using radians. If we're using degrees, sorry. We always need to use this degree symbol if we're using degrees, because otherwise a marker will assume that you're talking in radians. From now, we're going to be trying to transition towards radians as much as we possibly can. Now that we've gotten this key relationship, we're able to construct different angles in degrees in terms of radians. For example, 60 degrees is 180 divided by 3, so 60 degrees equals pi on 3 radians. 30 degrees is 180 divided by 6, so pi on 6 radians. If we want to convert between degrees and radians, we use this 180 and pi relationship. If we have an angle in degrees, and this angle here is in degrees, we multiply it then by pi on 180 degrees. And if we have an angle here in radians, we want to convert it to degrees. If we want to convert this angle in radians to degrees, we do 180 over pi to degrees. And so an example might be pi on 6 times 180 on pi. And so in this case, we cancel out the pi's, 180, and we get 30 degrees. Okay, and so these are the key relationships between converting between radians and degrees. And so as we can see, radian measure is directly derived from circles. Now we're going to move into circular measure then. We're going to have a look at the length of arc, areas of sectors, and areas of segments in a circle. What an arc is defined as is, as we've already defined it in that previous slide, an arc, if we define a point here and we trace out a line towards the circle, then this is the arc length. This here is the sector, and this is more specifically the minor sector. The major sector is the thing traced out here, and you can kind of see why it's called major versus minor. And then if we're looking at a segment, it's basically we cut out a line like this, and the segment will be this area here. Okay, and so if we look at the arc length in terms of degrees, if we want to calculate arc length in terms of degrees, generally what we do is we have our angle here, theta, and we divide that by 360 degrees, and then we multiply that by the circumference of our circle. If we're looking at the segment, and we have a area, then we're generally doing theta divided by 360 degrees multiplied by pi r squared. And if we look at a segment, generally what's happening is we have a look at that sector, and then we subtract a triangle here away from that. So we have theta on 360 degrees of pi r squared minus, using our area of a triangle rule, we get 1/2 r squared sine theta. Okay. Hey everyone, sorry I'm just interrupting my presentation, but I've just realized there's a bit of an error in one of the formulas. The segment formula should really be theta on 360 degrees multiplied by pi r squared, and then minus 1/2 r squared sine theta. So we have pi r squared minus 1/2 r squared sine theta. And that 1/2 r squared sine theta will give us the area of this triangle here. Okay. Now, when it comes to radians, we can actually streamline this process a lot. So this is a segment, sorry, just to make it clear, and this is a sector. When it comes to our length of an arc, so this is in degrees here, this is in radians. When it comes to our radians, recall that our angle in radians is defined as the arc length divided by the radius. And so if we want to calculate length of an arc in radians, we can use L, equals r times theta, because theta in this case is equal to L over r, and so the r's can cancel out. So r theta. If we want to calculate the area of a sector of a circle, then that's going to be equal to 1/2 r squared theta. And if you think about what theta represents, it's the length divided by the radius, which is 1/2 r squared L over r, which is equal to 1/2 RL. And if we think about that in terms of degree logic, that's equal to radius times the length, which is pi on 360 degrees times 2 pi r. So we can cancel these out. And we end up with the same 360 degrees times pi r squared. And so eventually we get to the same sort of definition. Just this, in this case, this is a lot easier to deal with than this. And this is just one reason why we use radians rather than degrees. Okay. And finally, we also have the segment. And this uses a lot of the same logic that we saw in the degrees section. So the area of the segment is equal to 1/2 r squared theta minus sine theta. Okay. So those are all of the circular measures. So 1/2 r squared theta minus sine theta, that's the exact same as this section here. You can see the pi r squared, theta on 360 times pi r squared is equal to 1/2 r squared theta. And then you have similar logic kind of here with the r squared times sine theta. Okay, cool. So we've had a look at the cosine and sine rules to find sine, cosine, and tangent in terms of the unit circle definition. Had a look at some of those rules. We've had a look at circular measure, introduced the concept of a radian. And then we've also used radian measure to calculate lengths of arcs and areas of sectors and segments in a circle. And so that is us done. I just wanted to let you know that you should subscribe so you don't miss any new videos, and comment if you don't understand a concept or I've missed something, and that the next video releases on the 2nd of November. So I'll see you guys then. Thank you.